I'm a professor at Utrecht University, and I occupy a chair in occupational hygiene and exposure assessment there. Since a couple of years, I also have another chair, which might not be of much interest for you, but that's on electromagnetic fields and health. Because in the Netherlands, they decided to start a very big program on electromagnetic fields and health, and I managed to get a fair share of that money. So I have two heads nowadays. As Jacob told you, he only told me after I think 4 hours waiting in the plane yesterday that he asked me whether I was willing to present here instead of John. Of course, I said yes, but of course I also ran out of my battery of my laptop already, so I couldn't prepare it. So what I did was I asked one of my PhD students to send one of his presentations. So that's what I'm going to present. This is work of Jelle Vlaanderen, who is, I guess, I know for sure, one of our brightest PhD students, and he will, that's him. He will graduate pretty soon in 2011 and on the 19th of April. And his research focused mainly on the use of occupational epidemiology in risk assessment. His work was financed by an EU network of excellence called ACNIS, also focusing on cancer. And what Jelle did was trying to improve the use of epidemiological evidence in risk assessment, either by applying new methods or by incorporating biomarkers, for instance, into epidemiology in order to improve the use of epi-evidence in risk assessment. This is his thesis. Most of the stuff has already been published. There are a few chapters that are still. He's still working on. Actually, he has to hand it in today, so he better hurry. What I'll be talking about is about flexible meta-regression to assess the shape of the benzene leukemia exposure response curve. Of course, there has been an awful lot of debate on that, and we try to put some fire in that discussion by doing a formal meta-regression of a lot of epi-evidence that is around on benzene and leukemia. He also developed other methodological tools like the guidelines that were to evaluate human observational studies for quantitative risk assessment. That's a paper that he published in Environmental Health Perspectives, I think 1.5 years ago, where he actually tried to come up with rules how to evaluate epi studies and to make better use of them by especially focusing on the quality of the exposure assessment of these epi studies, which in a lot of cases is, of course, the weak point in occupational epi studies. That was one of the reasons, for instance, why I was here yesterday, but I didn't arrive in time for the meeting, but to advise on the exposure assessment of one of those studies. And the other interesting tool that he developed with us was the tool to evaluate the overlap between work histories and histories of measurements. We all know that measurements were only done in more recent times, while the occupational histories of most of our cohort studies go back to the 30s and 40s. And he developed a very graphical and simple tool to get a feel for how much extrapolation is needed, for instance, and which studies have more and better coverage of the measurements with their occupational histories than other studies. Anyway, and he's working on a few other papers where he tries also to improve the epidemiological evidence by bringing in new technologies, omics technologies in the whole of the epi analysis. Okay, but I'll present now on the flexible meta-regression technique that he used to get more insight in the shape of the benzene leukemia dose-response association. You all know what benzene is, of course. What you also know is that it's nowadays an exposure that's more of concern environmentally than occupationally, I would say. Although, of course, there's still quite some people that are occupationally exposed, but especially the evidence and the focus has much more been on low exposures than on the higher exposures that occurred in the past. But most of the evidence is derived from studies where workers were really highly exposed to benzene. And on the other hand, of course, when it comes to hazard identification, for instance, in the IARC monograph program, it's most of the time just looking at exposed workers versus non-exposed workers and make a decision about what the evidence for benzene is when it comes to its carcinogenicity. As I said, the general population is exposed to benzene as well from different sources, but at much lower levels than in the occupational than among occupational workers, employees, and yeah, the interest has shifted to those low risk, and simple comparing exposed versus non-exposed is not that informative anymore for the purposes that we want to do our risk assessment for nowadays. So the focus has shifted to the dose response assessment. So we're going beyond benzene causes leukemia. We want to know more or less exactly how that shape of do I have a pointer? Yeah. How the shape of this curve is. Is it like this? Is it linear? What is it that we want to know, and we have to know because we want to say something about those risks at low exposure levels. If you look at and that definitely holds for the Dutch Health Council that set limits for benzene. What most of those bodies do is look for the best study, and most of the times they end up with the infamous pliofilm cohort study that is often used to assess the dose response curve and then extrapolate it to the lower levels. The problems and what has been done in the past is just linear extrapolation from those high doses to low levels. And the problems, of course, is that linear extrapolation justified or not? And as you all know, probably, that there has been an awful lot of discussion on the quality of that study, the pliofilm study, and especially its exposure assessment. If you just put all the papers together that has been written on that, I think you already have a thesis. But and what we are basically looking at is this: we have the points on our exposure response curve that are known from for instance the pliofilm cohort, where we have high exposures, but we want to go down. We want to know what the actual risks are here, and we can have several possibilities. We could have indeed a linear relationship also at that low levels, but we could also have a supralinear or sublinear exposure response relation, as we see here, or we might even have a threshold effect, of course, which has been hypothesized as well. So that's where the big unknown is, and we tried with the evidence that we got from other epi studies, try to shed some light on that. What are the issues with the pliofilm study? It was based, the exposure assessment was based on very few exposure measurements. All the data gaps, and there were many data gaps, were filled with expert judgment, which was, as such, of course, is not wrong, but it always leads in enormous room for discussion. And in this study, there was a large potential for exposure misclassification, and it has been argued by a lot of people that the assigned exposure levels were either too low or too high, and that they were not very accurate to start with. And therefore, with all these discussions around this study, and with the very high exposure levels these people had during those days in the rubber chloride industry, it's very difficult to decide what the actual value of this study is for risk assessment. So how did we try to improve that situation? We used all the risk estimates that we could find from relevant occupational studies to use all that evidence together to get a better idea of the shape of that benzene leukemia exposure response curve. And there are basically two ways, probably more than two, but these are the two ways that you could deal with it. You could either do it traditionally and do a traditional meta-analysis where you assume linearity within each of the studies and then derive regression coefficients of each of those studies and then perform the standard meta-analysis on those regression coefficients. The problem is then that you assume that everything is linear, of course, and you have no flexibility to assess the actual shape of that exposure response curve. The meta-regression technique that we used here does allow you to do that because it factually does a regression on all the aggregated risk estimates that you extract from each individual study. So you put all the individual risk estimates together and then try to fit the best fitting model. And that allows you to come up with a much more flexible regression model. And of course, a more, not by definition, linear exposure response relation. Yeah, we had some inclusion criteria, of course, for which studies to select. In order to do it, of course, the studies should have done quantitative benzene exposure estimates. And we needed, of course, risk estimates for leukemia because that was the outcome we were looking at. And we also took into account whether within the studies strong confounding factors were adjusted for. That was, of course, important. And we also needed sufficient details and design on the conduct of the study in order to see whether we could actually use that study. Jelle came up with, and he also used his own guidelines. He came up eventually with 11 studies that he could use. 9 of those were of sufficient quality, and he had to exclude further 2 studies that were either very poor on the reporting of what they actually did in terms of statistical analysis, or used a very undefined exposure metric when it came to assessing the exposure to benzene. And here are the 9 studies that he used. What is it? Yeah, 6 of them are cohort studies. 3 of them are nested case control studies of the petroleum industry, the infamous Australian Health Watch study, the UK petrol study, and the Canadian petrol study. And the others are different cohorts. Some of them also, I think, most of them are chemical industry, I would say. Yeah, some of them are Dow studies, like the one from the Netherlands, and there's another USA Dow study. There's the ply film study, of course. But the nested case control study are mainly coming from the petrol industry. So from these 9 studies, he extracted all the risk estimates relating cumulative benzene exposure to leukemia, and he either used relative risk, odds ratios, or SMRs when they were reported. And of course, the risk estimates were reported for exposure categories, and they were most of the times defined by both a lower and upper bound exposure level, or only a lower bound, for instance, above for the highest category. Often you see above so many ppm years. And of course, that had to be translated into to actual exposure points. And here's an example, for instance, of one of those studies. You see here everything below 1 ppm is used as the reference, 1 to 2, etc., and then the highest category is 16. But in order to use these odds ratios, we had to come up with some kind of point estimate for this category. So the traditional method would be to just use the midpoint, calculate the midpoint of these categories. For instance, like in that first one here, from 1 to 2, you would take 1.5 as a midpoint. But we found that too crude, and we tried something more sophisticated. And of course, you also have a problem with that approach when you go to those these categories, because where do you take a midpoint when all you know is that it's above 16? That's a problem. So what we did, we assumed a log normal exposure distribution for each of those categories, and we extracted information from the studies to get insight in the exposure category and the distribution of the exposure within that category. And we did that by looking at the controls or the number of person years in each of the exposure categories, and then we fitted a probability density function on the available data, and use that to predict our geometric mean. And here you see everything put together. We were able to extract 30 risk estimates, and as you see, the highest exposure category is here for the plyofilm cohort, where you have something like 550 ppm years. And you see also that there's an enormous amount of data points down here at the very low levels. And that's of course where our interest is, so we were quite happy with the fact that we had quite some evidence at those low levels of exposure, cumulative exposure. And you also see that the petrol industry, the blue ones are at this low end, while the chemical industry and the older studies are more at the higher end of the distribution, as well as the Chinese study, the NCI study of Shanghai, I think it is. So this is what we got, and we tried to do the meta regression on these estimates. We had to do a few additional things that are, statistically very important, but probably of not much interest for you. We had to allow, of course, weighing for the amount of data the estimates were based on, of course, and we took that into account. And we also had to take into account that, especially within the cohort studies, where internal comparisons were done, of course, everything was relative to a common reference group, and that made the estimates dependent or not totally independent from each other. So we had to do some adjustments for that as well. Then the regression models, we could do a linear regression model, of course, to see whether there was linearity at all or not at those low levels. And the other way we did it was by applying restricted cubic splines, where we used 3 knots and a random effects model to allow for heterogeneity between the studies. And here are some examples for what kind of curves you can estimate with such a restricted cubic spline. So it gives you an enormous amount of flexibility to actually let the data decide what the shape of the exposure response curve is. We used logistic linear models where we took the log of the relative risk or the odds ratio versus the exposure. And we did that because it parallels the results from normal logistic modeling that you would do with personal level data. And it also gives equal distances between the risks. So you get as much distance between a relative risk of 2 and 1 as between 0.5 and 1, which is something you want, and overall it gives you quite good statistical properties. So this is what we got with the best fitting models. The black one here with the black confidence interval. So what you see here is the black one is the linear one, and here is the best fitting one that shows a supralinear effect which is topping off at higher exposure levels. And the flexible models show that it's definitely not linear. And another complicating factor is that both models predicted an intercept. So they both don't go through the origin, what you would expect. Without any benzene exposure, you would expect no increased risk, but that's not what we saw. And there are reasons for that. So we actually see a supralinear shape, as has been hypothesized by others in the past, and the idea behind the superlinear shape is that it has to do with the saturation of the benzene metabolite enzymatic pathways that are underlying the whole process of benzene leading to leukemia, and that might be responsible for that superlinear shape. And the attenuation of that response curve at higher exposure levels might directly be related to the depletion of the susceptible individuals at the high exposure. You don't have susceptible individuals anymore, so that's why it goes down. Or it could be due to exposure measurement error, of course, because higher levels are probably estimated with more error. It could be a healthy worker survivor effect, or it could have to do with high disease background rates. That's another explanation for what we're seeing at that high end. The intercept, one of our conclusions is that we're estimating an intercept because we had reference groups that were not included in the analysis. We couldn't do that because they had no exposure, of course. And we also had relative risk for non-reference exposure groups that might have been increased due to non-benzene exposure related factors, of course. And it also could be that those very low groups with low exposures already had an increased relative risk, of course, above the background level. That might have been another reason. But since we didn't have really unexposed people within within those studies, we might see that intercept that we're estimating with our model. We also did sensitivity analysis, like what does one study matter in this all. So we just took out one study, repeated the whole analysis, and then compared the results to the overall. So that's what you're seeing here. You see different curves, but it's all of them are without a particular study. And the two most important studies in terms of effect they had on the overall estimate were the NCI study, the Chinese NCI study, and the pliofilm study. So when you exclude the NCI study, the risks are predicted much higher, and so the risk for the higher exposed groups go up. While if you exclude the pliofilm study, the risk at the higher exposure levels actually goes down. So these are very influential studies in this exercise. When we stratified by study design, we saw something very awkward. The nested case control studies showed a totally different shape from the cohort studies. That's the blue line here, where the risk went up very dramatically at very low cumulative exposure levels. You all know probably that's probably driven completely by the Health Watch study that showed very high risk at very low levels. Well, for the cohort studies, we see basically what we saw in the overall analysis. So the question then arises: are these case control studies, these nested case control studies, systematically different from the cohort studies? There's scientifically no basis to assume that there are fundamental differences between nested case control studies and cohort studies. That there shouldn't be. The only difference here is that the nested case control studies come predominantly from not predominantly, only come from the petroleum industry. Sorry, and they only provide information on very low exposure levels, where the cohort studies as such have very limited power because they had people with much higher cumulative exposures. So you have the case control studies on the lower end, while the evidence for the cohort studies is more directed at the higher exposure levels. So how could you use our findings in dose response assessment? Here we give you all the options. Basically, you can do what you want, what you think is right. So we didn't claim that we have the answer. We know what the best fitting model is, but still, you can fit whatever model you want. You could correct for that intercept that we saw and force it through the origin, and then you get still a superlinear shape, as we had here in our best fitting model. But then at least you're not predicting any risk for people who are not exposed. You could only use the cohort studies, then you would have a much lower intercept, and then the curve would be something like this. And of course you can still force it through, even with the data that we have, you can still force it through the origin. And then you get a shape like this. And what you see is that the difference is not that much at the higher end, you know, because the relative risk for people here above, say, around 500 ppm years is something like 1.5. It's 1.4 here. It's 1.4 here, and only here it goes with a linear extrapolation. It goes up to 2. But the real difference, of course, is at the lower exposure levels when you go to, you know, to something like 10 ppm years, something that would be very normal nowadays for a worker, I think, in an industrial exposed situation. After a couple of years, then you end up with quite different estimates of the risk. By the way, these are logs, so you have to put it to the power of e before you actually get the relative risk. So these are relative risk of what is it? Something like around 4 or so. So the difference is at this very low end where you predict much higher risk when you actually use the superlinear exposure response curve than when you use the linear one, as you can see here. So the risk here for 10 would be much lower, for 10 ppm years, much lower than.
Excuse me, can you talk a little bit louder?
Sure. So that's basically the difference at the lower end of the exposure response curve. Our conclusions after this exercise, we think that this flexible meta regression offers a very efficient approach to get insight in the benzene leukemia, those response relation, but that could hold also for other exposure response and those response relations, of course, because it makes you, or it allows you to make use of all the evidence that's there, and you can still, you know, apply criteria to the quality of the studies that they have to adhere to before you actually make them part of your meta regression. But still, you can make use of all the information instead of, you know, choosing the best study, which is often not good enough. That's our main conclusion. Except Jelle, there are a couple of other people who put a lot of effort into this. One of them is Lutze Portenge, who did most of the statistical work, and Rolf Meulen, who is his supervisor. And then there are the people from NCI that played a major role in his work as well, Qing Lan and Neth Rotman. Thank you very much.